Is it a good morning for you? Okay, so good morning everyone. And welcome to the Inter-University Center for Astronomy and Astrophysics, which we lovingly called IUCAA. It is a famous research center for the subjects astronomy, astrophysics. And across the world, there are many people who have studied here, researched here, and now they are working all over the world as well. There are several great scientists who have been pride of our city, of our nation, who have worked here in this institution. You might remember, of course, Professor Jayant Narlikar, who recently passed away. He was the founder of this institute, and of course, also a scientist who believed in sharing the knowledge that he has and sharing the work that is done at IUCAA. So, in that spirit, over 30 years, we have conducted this series of lectures, and you are part of one of them. So, it's a historic thing, it's a memorable thing that you are part of today. This series is called the Second Saturday Lectures, and in this, we try to bring to you some scientists, some people who work in science, who use science practically, put it to some work. And these people come here, they narrow down the field of work that they are in, and they simplify it for you all to understand, to appreciate, and also to probably get inspired, right? So you have this excellent chance today to meet an astronomer, a young lady astronomer who is part of IUCAA, and she has recently got her PhD from this very institute, and I'm sure she will share her past and experiences of her student life, and so you can take hints from her in what you as school children can do, so that if you are inspired to do research in science, and in particular in astronomy, you can follow up on that. So again, thank you for being here, and we are now going towards the lecture. This particular lecture is on astronomy, but with a different perspective. So it is about some different kinds of radiation, light that comes from the sky, and our speaker today has been studying that here in IUCAA along with some other scientists, and there is a very big group of X-ray astronomers in India. She is part of that, so we are very proud to have her here, and so let me welcome Dr. Parisee Shirke to the stage.
So I'll get started right away. The title of my talk is Astronomy of the X-ray Sky. I will first start with X-rays because I think that's what everybody will be familiar with. Then I will take you to the X-ray sky because that's what I'm primarily interested in. Then I will extend this to how we do astronomy with the X-ray sky and how we study this X-ray sky down here on Earth. Finally, I will take it down to how Indian institutes carry this out with a special focus on the work done here at IUCAA. And finally, I will try to emphasize how students can also derive from this, because this is a second Saturday lecture. I will try to render it to your specific age group. So starting with X-rays, these are two main applications where we encounter these every day, airport security centers and medical radiology units. Typically, this is where we encounter X-rays. But now let me take you to the sky. This is how the universe appears in optical light, like we're seeing each other right now. If you go and see the sky, this is how it looks like. But the X-ray universe is slightly different. So this is how, if you take your airport security center unit or your medical radiology unit and then see the sky with these X-ray eyes, then this is one of the latest images of the X-ray sky that we have. And this is what I tried to study as an astronomer. The main reason why I like X-rays is that it gives us an insight into the powerful hidden mysteries around us. So like airport security centers, and they can see inside your bag using X-rays. Or in medical centers, they will use X-rays to see the bone structures inside your body. This is like the skeleton of the sky of the universe that we can see out there. It reveals a lot of hidden mysteries to us. And what is even more interesting is these mysteries are not like simple in their nature, they're quite powerful. So some of these X-ray sources can give out so much energy that they can be as powerful and as about 10,000 suns. Okay, so the sun is a very powerful source. We get only a minor fraction of this sun, and even in the summers we start feeling hot. Now imagine what kind of power must be hidden in these X-rays, which we would not have been able to see had we not been specifically interested in seeing the X-ray sky. This was how we encountered that there are sources of X-rays in the sky. So some X-rays were expected from the sun, but to a limited extent because it's very close to us, it's very hot. But at the same time, no other primary sources were expected from the sky because we were not expecting anything to get so hot and so energetic, to throw such energetic and powerful radiation towards the Earth. So it was a surprise when they sent out a rocket for some other purpose, but then they saw a very powerful source of X-rays coming from the sky. Now, if you see here, the source of X-rays was not small. If this is the size of the moon, so you can see, imagine how large the moon looks in the sky, then this was almost as big as that. So it was almost as big as the moon. But you know how close the moon is to us. Meanwhile, these sources, there is nothing of this sort very close to us. So now you can get a feel for how powerful these sources might be, that even at such huge distances, they appear as big as the moon in our skies, provided you have the right X-ray vision to see this, like Superman, for instance. He has X-ray vision, so he can just see in the X-rays. So provided we had that sight as well, then we would have seen probably a second moon of this sort. This was in the Scorpius constellation, so it's called Scorpius 1. But once this discovery was made, we progressed on to more sources. The first thing, the question that came to mind is what's causing these X-rays? Because our existing knowledge never pointed to any mechanism by which the sky could produce such heavy X-rays, you know. So that straight away pointed to maybe objects like neutron stars and black holes, which are responsible for a lot of extreme physics that we know, because only such very highly compact objects could maybe produce such highly energetic radiation. This is something I drew out from an encyclopedia, which I once went through as a child. And you can see the picture that they actually had for a black hole was actually something of this sort, where there's a second star over here, and matter is falling from that star going towards the black hole at the very center, and you have X-rays coming from the innermost part here. This is an X-ray image of like a neutron star related object. We'll see more. Now, when you have a neutron star, it has a heavy magnetic field, and it interacts in a way where the final object that we see kind of pulses about in the sky. So it's not a stationary image like I showed you before. If you keep measuring the sky and continuing to see it in the X-rays, then it kind of flickers at us, like it grows in intensity, goes back out again, or like a lighthouse in the ocean. So it goes around and you see it in this very specific manner. I like it, so I study these objects, they're pulsars. And in X-rays, you have X-ray pulsars. So the same objects, pulsars can be in any band, but here, if they are seen in X-rays, then they will give you X-ray pulsations. So your X-ray sky is not stationary again, or it's not stable. You have some sources which are pulsating, some sources which just come up and then vanish again. So it's a changing picture. It's not a fixed X-ray sky that we have. Astronomers often measure how some of these sources vary. So some of them can show up and then die down, but pulsars are pretty regular, so they keep going, blinking at us for a long amount of time. This is, again, it shows some of their blinking nature in highly energetic radiation, and this is the blinking pattern that we have here. Now this is one of those images that I have. This is the crab pulsar. It was there in that encyclopedia also. The crab pulsar is a nearby pulsar, but it's an isolated one, so there's no star near it from which is accreting matter. This is a newborn pulsar, so because a star died and then there was a supernova, it was such a violent and energetic explosion that the remnant is formed is a neutron star, and it powers very highly energetic X-rays, and that's why we see it as an X-ray pulsar. Along with that, you have other types, for instance, because if you have binary X-ray pulsars where there's a second star around it from which it's accreting matter and then powering those X-rays, then you can have more and more exotic and interesting types, like transitional millisecond pulsars, for instance, where the purple radiation is in X-rays, then it stops, it switches mode to something else, and then it again returns to X-rays. You also have something like black widow or redback pulsars, where again, if the purple jets are pointed towards the companion star, then it's so powerful and it's so energetic that it can actually start evaporating the companion star. Again, if the central object is a black hole, like it was shown in an encyclopedia, we get black hole X-ray binaries. Binary just points to the fact that it exists in a couple, basically. Over the time now, we have studied the X-ray sky more and more. So although it started out with X-ray binaries and our knowledge of neutron stars and black holes, over time we have detected a lot of different kinds of X-ray sources in the sky. So it's far more interesting than it used to be. And our knowledge about these sources is also growing with every study that is being conducted. I have enlisted all these sources here. Some of the more, which I thought are more commonly known, have been highlighted. I find one of the planets in our solar system also shows X-rays in their aurorae. And this is something called X-ray bursters, for instance, which can give you some temporary X-ray flashes if you have some material temporarily coming onto the neutron star. Now coming on to how we study the X-ray sky. So all of these things are happening, but when we do astronomy, we need to be thinking about other things about how we go about studying this X-ray sky. So if you take X-rays themselves, for instance, because that's where you're going to have to start, where are we right now with X-rays? Okay? X-rays is a very rich field in physics. It's connected to fundamental physics concepts and principles. A lot of Nobel Prizes have been awarded to advances in the field of just X-rays. Okay? This is not astronomy. This is just X-ray physics, basically. This is a chart I found at Ferguson College. They have a list of Nobel laureates over the ages, and I have put a green square around those which are related to X-rays. And each one signifies a major advancement in the field of X-ray technology that we know of. This is a picture from the staff room. They have a physics museum in which they have these X-ray tubes that used to be used in the previous century to make X-ray measurements, so which later on advanced. Because see, this first guy who got the Nobel Prize, the very first one, was given to the discovery of X-rays, and Marie Curie, who everyone knows, she's a double Nobel laureate, physics and chemistry, pretty cool, but she championed the application of X-rays to medical purposes. So these were some early X-ray tubes that they still have. But now we are interested in the astronomy part. So how do we take this and then try to do astronomy with it? So this is where we're going to focus on the cosmic X-ray sources. Now this was done somewhere in the 1970s, and it was awarded the 2002 Nobel Prize again. And this time, this is the one Nobel Prize that I will be focusing on for the rest of the talk. This is the Nobel citation. If anybody is interested, then the Nobel lecture is available online, and you also have the transcript of the Nobel lecture. If at any point in the future also you get interested, then you should know any Nobel Prize, you have a lot of the Nobel lectures, and their transcripts are available online. So how did they go about this? They were awarded the Nobel Prize for the discovery of cosmic X-ray sources. How did they manage this? What was the major advancement for which they were awarded the Nobel Prize? So first and foremost, if you're dealing in X-rays, you have to be in space. Not because you cannot have X-rays on ground, but the cosmic X-ray sources although they're emitting a lot of X-rays, those X-rays get blocked by our atmosphere at a very high height. That's how they're never a health hazard for us, right? Otherwise, X-rays can be very hazardous. Even in the hospitals, they will make sure you are given a very limited exposure, otherwise they are harmful. So while we can do terrestrial X-ray studies, we cannot do terrestrial X-ray astronomy, because now you're dealing with the X-ray sky, and anything that's coming from the sky and was not generated down here on Earth, you cannot directly view from below, like from here, the surface of the Earth, because it's not going to come down from the atmosphere. The atmosphere will block it. So now it is absolutely mandatory for you to send out something to the top of the atmosphere. So then you will be able to measure some of the X-rays that are coming to you. These are some of the early efforts in space tech that were made, some space missions, and we'll see more of them as we go on. A major boost, so once they demonstrated the capabilities of such a space-based X-ray study in the 1970s, then in the 1990s came a major boost where there were more and more focused studies with the launch of the NASA Chandra instrument. I've shown it here. Fortunately, we were able to study these kind of techniques later on towards higher studies where we had dedicated courses on this. And I've tried to include some pictures here that helped us really grow our knowledge of these objects in the sky in a major way. So if we thought the Crab Nebula out there was like this, then in the high energy I showed you it's like this, and that's how you know that at the center, because it's only coming from the center, the X-rays, you have something of this sort of a structure, and again that confirms that it might probably be a neutron star. This is a picture of gas present in clusters. So it's not necessary that your X-rays only have to stay confined to neutron stars and black holes. Like I said, variety of sources are giving you a wealth of information. You have specially designed telescopes, keeping in mind that these are X-ray detectors. And here, if you see, then this is how, suppose we expect galaxy to look like. Then in the X-rays, it sort of looks like this in the Chandra readings. So your X-rays really make it visible for you what's the heart of the activity that's going on in the object that you're looking at. A lot of telescopes have since then been launched up till date. So let's bring it to the 21st century now. Several telescopes, because the field just expanded, and there were so many people interested now knowing that there are so many objects out there that can be studied. This was a slide that we had shown in National Science Day, but I thought it's a good summary to show you as well. There's a nicer mission. ISRO has also been sending up X-ray missions, and X-ray people are most excited about astronomy because they cannot work from the ground. So everybody can, like GMRT can be on the ground. You can still have optical telescopes on the ground, but X-ray sky, if you want to study, it needs you to get to space. There are future missions planned. This one has already gone up a few years back. There are more in the pipeline, and I'll give you some view. The achievement of space tech is a rare capacity. Very few countries are space enabled today. So if you are space enabled, then it's a very respectable facility to have, breeds a lot of respect, and very impressive. And the nation as well is trying to go in a direction where we're trying to improve our knowledge of the third dimension, basically, where we have deep sea and deep space studies increasingly. So these will again gain more impetus. Like I said, because I was studying the X-ray sky, I had to keep tab of the space missions as well. So as students, this came on the front page, but this was on Chandrayaan-2 mission. You get to deal a lot with space if you're working in X-rays. These are some of the participating institutes that then come into play. Astronomy is a very necessitates collaboration. It's difficult for people to do it all by themselves because of the funding, technology that is required, so it breeds partnership. You have lots of institutes here. The way they measure is they'll send their own space satellite up here, and then the system you have basically that is emitting X-rays, you record those X-rays with your space mission that keeps orbiting the Earth, for instance. Then that data gets telemetered to the ground, and then it is analyzed by somebody, by the required specialist, maybe at ISRO, or you had this cell at IUCAA, and then it finally comes to you, who are the astronomers. Okay, so you can do science with it, and you can have like clean data to look at. Again, because you're dealing in X-rays and you're making space-based measurements, they have like dedicated special software that has been developed to analyze this data. So I had to get a feel for learning this as well. And again, I showed you one X-ray telescope before. This is another one. A special thing about X-rays is, which you'll come to like maybe in higher studies, you'll study this, but they behave like photons. So it's radiation, so they do behave like waves, but at the same time, X-rays behave like photons, basically like catching cricket balls. So this detector is supposed to do that. And like we have a rainbow, we have 7 color bands, right? Vibgyor. So the X-ray band is divided into soft band, medium band, and hard band. So you have like a tricolor rainbow for X-rays. Now coming to IUCAA, these are some of the screenshots of the web pages that are available on the IUCAA website. X-ray astronomy comes under high energy astrophysics. High energy basically points to you're dealing with highly energetic radiation, because you also have like gamma slightly radiation coming in, so it's clubbed under a high energy radiation title, and X-rays is a subset of that. This is IUCAA's participation in the AstroSat mission. Something more you have is there's an international astronomical union that tries to make sure that all of these countries are collaborating with each other. And Division D deals with these high energy phenomena and fundamental physics, because a lot of these high energy phenomena directly point to and require a knowledge of fundamental physics. So another exciting part that we have is, because it's an international collaboration, any work that you do here, see, the sky is common to everybody, okay? The sky doesn't shine differently for different people. It's up to you whether you want to study it or not. So anytime an astronomer tries to study the X-ray sky, you can collaborate with other scientists all across the globe who are seeing the same sky, and then try to further your science. The way this works, for instance, is there was this Cambridge Astrophysics series book on X-ray binaries, and one of the authors is an honorary fellow at IUCAA over here. And by sitting and doing work here, we were able to get our work across to him, and then he appreciated the work in turn, and so on. So you remain in a global setup. Again, my own supervisor had written a chapter in this book, so I got to work directly with him, and it all builds a global experience of working, so it really broadens your horizons as a person. We also had a former director of IUCAA who was an X-ray astronomer, and he used to try to make use of multi-wavelength studies, where he would put X-rays with other bands, for instance, and go deeper. But to progress now and give you an idea about where we are at, like today, okay? X-ray astronomy, I mean, you can do various things with it. You can see how the sky looks. You can see how it changes. You can see how it is divided into its rainbow colors, like soft, medium, hard X-rays, for instance. But now all of that has been done to a fair degree. And today we are standing at the precipice of a new technique in X-ray studies, which is opening, and that is X-ray polarization studies. Again, because you can have terrestrial X-ray sources that you can study terrestrially, X-ray polarization studies can be carried out for such sources as well. And here, irrespective of what the source is, polarization studies try to help you study the magnetic nature of these systems. If you're going to have magnetic sources in the sky that are emitting in X-rays, then you are looking at X-ray polarization studies of these systems. And for this, again, because the atmosphere will block all of this, you need to come up with special technology that will help you do this, again, out there in space. So far it had remained a technological challenge. But this has come up, and a lot of news henceforth will deal with polarized X-rays. Like I have one example here of work done by people at IUCAA. And again, in a first, AstroSat detects polarized high-energy X-rays from a black hole. So in a first, because this technology was really out of reach so far, and a lot of scientists today are looking at making these measurements and studying the X-ray sky in this particular way. Now coming to some of the work which I did, to give you some fair idea without going into too many technicalities about how some of this work actually looks like. I studied a source called Centaurus X3. It's in the Centaurus constellation. I'll show you some pictures again. But this is what I was looking at on my computer. So they sent AstroSat up. They had this X-ray detector, which I showed you initially, like a box, and it catches all these X-ray photons, okay, in the sky. You point it at Centaurus X3, you count the X-rays that are coming from Centaurus X3, and they kind of looks like this, okay? So because it's a pulsar, they pulsate. The count is not constant, so initially you catch more balls, then it goes down, then you catch more X-rays, it goes down. So it was nice to see the pulsar on my screen. And this was a slide that was shown by Riccardo Giacconi in his 2002 Nobel lecture, which I showed you initially. That's the Nobel Prize I'll be focusing on. So these exact pulsations were shown to him by him to a global audience, and you can see that they're similar in their nature because these are also Centaurus X3. Again, if you see here on this graph, the broad nature of these X-rays is also slightly different. So pulsar aside, your neutron star is kind of revolving around the binary star, right? So it slightly comes towards us and then goes back away from us as it, like the Earth revolves around the sun. This thing is revolving around its binary star. So you can see that some of its X-ray count kind of grow and then wane in flux. So these minor things could be easily checked by me, and it was really interesting for me to see them. If this is Centaurus constellation, then somewhere here is Centaurus X3 that does this, basically. So this is the source you're looking at. Now, we're here on Earth, and what do we do? So we have different facilities with which you can see this in the sky. Okay, so for example, if you have this observatory in the US, then it sees it in the optical, which is the visible, like we see each other. And this portion of the sky, they see like this, okay? Meanwhile, there is another observatory here in Chile, and they see the sky in a different way. And when they see this patch of the sky, they see like this. But what's special about X-rays is once you send up space satellites up, which can measure in X-rays, they see the sky very differently. Like I showed you in some of the initial skies, the visible sky and the X-ray sky, very different. So AstroSat sees this portion, something of this sort, and you have this by another NASA telescope doing this, okay? So you can see how different the X-ray sky might be. Do not go into the technicalities of it, but just to give you an idea, you have this main star from which you have this neutron star. This is your source, and then you're seeing it using AstroSat on Earth with the help of all these institutes that help astronomers arrive at these conclusions. And this was the source again in the sky, and you can see how brightly it's shining in X-rays and outshining all the other stars that are remotely close by. What does a student get to do with this? So after 6 years of work, you get to write a thesis and you get to submit it to the library. I tried to, because I was interested in this hidden nature of the X-rays, I also had a secondary document for my thesis, which I call the X-ray version of the thesis, because it's like, it has more info. And then it gets uploaded on what is known as AstroSat PhD repository. Basically, it's a collection of all the theses that have been done with AstroSat, and then a global community gets to see it. Do not go into these details, just view them. But what I would like to share is this, for instance. If those of you who may have seen Mangalyaan, like Vidya Balan's character is believed to have been based on her. She's a major person at ISRO. And another thing I wanted to mention is through my work, I got to interact with some of these people, which was very interesting. Also because Again, like it's collaborative, I showed some software that was NASA software. So NASA featured all of the work which we did with AstroSat on its own website, so I got to go in there as well. And I also did some public outreach with this. It was especially interesting for me for rural outreach when I tried to show some of this work to teachers and other school students. They found it to be truly interesting. I have also some videos uploaded from my own end on YouTube, on the Life Around Science YouTube channel. This is a picture I have from one of the previous IUCAA National Science Days, where a student had tried to burst the myth that X-rays in the space will affect us in some way. They will not, because they do not quite reach us. Again, to give you a feel for how then astronomers go about their work, once your work is complete, you can go and share it with other astronomers. Do not go into the details again, but here maybe you can see conferences are organized, posters are circulated, and all scientists who are currently in the field can gather and share their work, so you get to benefit from other people's works as well. Now, coming out of the technicalities a bit, having given you some picture about what I have at my end on astronomy of the X-ray sky, here are some books which are good summaries if you'd like to go into them at a later point. These might be too advanced slightly at this level. But you have the X-ray universe, exploring the X-ray universe here, the universe in X-ray, some standard books that summarize how the X-ray sky looks and how astronomy is done to study this X-ray sky. Another thing I get asked whenever, the last time I gave a talk here to an audience, they asked me what some of the applications of astronomy are. And I would again like to highlight that the IAU is making an active effort to enlist these applications of astronomy and try to get them to people, so you can run a quick Google search and get them out now. So next, how is all of this relevant to you? Because you're like, okay, fine, so we saw a movie, but where are we in all of this? So just to give you a slightly different perspective now, the UNESCO has been trying to emphasize the importance of higher education on a wide scale now, and education system is divided into multiple levels today. Very complicated, intended to make it personal and suitable for us. But I'll give you some idea about how the progression of an astronomer looks like when they go about making some of these studies. And hopefully through us, you will get some feel. So it's not about enlisting our journey, it's about you getting to see our journey so you can take the paths which are beneficial to you. Here, if you see, this is your 10th grade studies. My brother, who's clicking photographs right now, he's also an astronomer here at IUCAA. And both of us chose to specialize in pure sciences because we were drawn to the whys of the universe. So trying to explain the phenomena we see around us, so we pursued bachelor's in pure sciences. Up till 10th grade, if you see, it was quite interesting when he pointed out to me that we were doing fairly well equally in the objective sciences. So your teachers maybe nominated the scientifically minded students, so I'm hoping that you would also be objective thinkers. And we graduated, we left school quite well. I was the science topper, and he also got multiple science and math prizes. Next, 12th grade, what does 12th grade have in store for somebody who's looking to make scholarly contributions in science? So you can, again, graduate, leave with flying colors. We have done our college from Ferguson College. Our school was SPM English School. I'm not sure if they're here. Oh, you're here? Good. And yeah, there's also this book called Dahawi Diwari, which is tries to have model answer papers for board exams, 10th and 12th. And I wrote the mathematics and chemistry papers in there. Now comes after your 10th and 12th, there will be something called undergraduate programs. Now there's a whole option, and we get a lot of questions on what undergraduate program should we choose that will lead us to the destination that we would like to get to. So what do undergraduate programs have to offer? Both of us did BSc, that's Bachelor of Science, majoring in physics, mathematics, statistics, with subsidiary subjects in chemistry and electronics. Do not go too much into the details because it will be slightly early for you. But just to show how the higher education trajectory takes you, he eventually went on to be, at the end of his BSc, All India Rank 1 in the IIT JAM entrance exam. So there were a lot of interviews being conducted, and that is something that can be quite rewarding for a student. Whereas I became the gold medalist for Pune University. So that is another way in which you can explore academia. Finally, at the end of your master's degree, you can again do well in your core academics. And if you do, you can probably have the head of your institute rewarding you, or they can bring in special chief guests to reward you. It's a very proud moment for parents as well, whereas you can just fight it out in your GPA at times like I did. And finally, the ultimate end is a PhD in the higher education system. That's the highest degree anybody can earn. He recently submitted his pre-PhD thesis submission seminar, so he's about to complete his. I completed mine a year back, and we were on the notice board at the same time, him for his submission and me for this talk. And this is his supervisor showing us, discussing some of our doctoral work. I do X-ray sky. His work is slightly different, but we've tried to keep some overlap to keep things interesting. But basically, when you're here, that's the end of the formal education system. And I hope I've been able to convey, to some extent, what the local ecosystem currently has in store for students who try to take this up for making quality scholarly contributions in science. Another something that you then do is something what I'm doing right now, and I'm hoping that you take that from me today, is once you have done your fair bit of duty, you then try to go back and pass it down to others, okay? Because the social responsibility is also a big thing. IUCAA has recognized that through the SciPop division and through the work that they have been doing, motivated by Professor J.V. Narlikar. I personally have been doing that by going out and giving public talks, but recently I went back to college, and then I'm again interacting with people who are at the master's level, UG level. Today I'm talking to you. Next week I will be talking to slightly 6th and 7th graders. There will be interviews that will be conducted, and yeah, there's more in the pipeline. So I'm seeing that a lot of them do benefit from having an intermediate level person around, and the professors are also quite happy that they have an interim person around. I would like to dedicate this talk to the late memory of JVN. Professor Narlikar's chapter in one of our science textbook was, I still remember it, our science teacher had told us he's a major luminary in astronomy and astrophysics, and his chapter was on the GMRT. So I came really full circle today, standing here on a stage where he himself used to give talks, and hoping that this might motivate some of you as well. And something at the school level, some activities which are conducted, you'll get to see how those are essentially progress down the line as you go on to higher education, and why they are being conducted in this nature right now. So you'll have like quizzes being conducted where they ask you to like scramble words together, or come up with different ideas or quiz questions. So these are basically intended to test your scientific faculty, for instance, because at a very young age, relatively, it's difficult for them to figure out who will grow up to, be somebody who could be really promising. So this is a way of identifying at a younger stage. Why are these important? Because finally doing science requires you to be doing some level of pattern recognition and seeing the order or patterns in the chaos around you. Okay, so you have a lot of information, but now in order to do any science or physics with it, you kind of see how they work together. So in order to do that, there's this book, The Universe Speaks in Numbers, and perhaps even in letters. So you have all of this to try to examine how your brains are processing this information, basically. And hopefully that is a good pointer of the scientific faculty of a person. I have some bonus slides as well later on if we have some time. But for now, I would like to leave at this slide. I'm not trying to motivate you towards the zodiac, but I just wanted you to appreciate the creative aspect of the X-ray sky. This is on a website I found by a fellow colleague. He was a British student here at IUCAA. He was visiting. And he has this very nice website where he does, along with the astronomy he does, research is a very creative endeavor because you're trying to do something new. And he tries to balance his studies with drawings and paintings, and he comes up with these and uploads them on his website. Recently, along with some university professors, they have suggested this X-ray zodiac project. So like we have in the visible sky, some stars distributed here and there. And then you see patterns in them, and you've divided them into constellations. And around the year, you have the corresponding zodiac. These people have tried to take groups of X-ray sources that you see in the sky. So forget the sky that we see. You take the X-ray sky as we see it, and then divide it into groups of stars, and then see all over again what shapes you imagine with them. So here you have the raven, which is like a crow. Here you have the bat for this. Here it's a dinosaur / raptor, and they have like more such. I showed 3 examples, but it's quite cool to see what they've been doing with the X-ray sky. Again, just the disclaimer, I'm not trying to push you towards the zodiac, just appreciate the creative aspect of this. Okay, so I can take a quick break because I can see you all getting slightly restless. So if there are any question answers, then we can go into that.
Okay, so students, I believe that you have seen something about the X-rays, which you know in a different way, but in astronomy when we use it, you see we get to see a very different world. Similar thing happens with different wavelengths of light. You might be knowing all the spectrum now, beyond the visible spectrum. So this is one way of, Parisee told us about how X-rays is being used in astronomy. So I hope you have caught up with most of the lecture. I believe that you might have very good questions to come up with. One by one we'll take up the questions. I want everyone to be quiet because I can hear and I have received a small complaint that people from behind are causing some trouble. This is what I don't want. I'm telling you, if we find any trouble with any of this school, we are debarring that school from next time to come here. So please make sure you do not make any noise. If anyone of you are not interested, just be quiet. Do not disturb others while the lecture is going on, because there will be many who will be interested in it. Fine? So let us take up some questions. Please raise your hand. We have Mate and Tushar who will come up with the mic. So please raise your hand. One by one we'll take few questions. Yes. Yes, you can ask your questions. Yes.
I am from Mahabir Public School. So my question is that what are demerits and merits of X-ray? If there is a demerit, how can we resolve them?
Okay, so the obvious demerit is that they're harmful, but all of this work is then done in a way where you try to keep it safe. So if it's done in hospitals, for instance, they will make sure that the exposure that a patient is subjected to is limited. So we never really go close to the harmful territory. Even in space, because these are space measurements, they're not really harmful to Earth. So the atmosphere completely protects and shields us from the X-rays which are coming up, which is why when you're going to want to study them, you need to send your detector out to a distance. And then, like we speak on a cell phone, that data will get telemetered down to the ground from a distance, so the X-rays remain there. Right? The only harmful aspect though, so when say Astrosat is going in an orbit around the Earth, there is a region called the South Atlantic Anomaly region, and that is heavily laced with charged particles which are very harmful to the detector. Okay, so while it's nicely detecting X-rays, these charged particles can completely disrupt its operation. So when the satellite is passing through that region, it will temporarily be asked to shut down and then start again when it's out of that region. But as far as the X-rays themselves are concerned, the detectors and instruments themselves are made in a way where you get to conduct your studies while measuring those X-rays in a reasonable and suitable way. So we never really go close to the harmful zones. But if you just ask me, are X-rays harmful? As a common person, I will immediately say yes, and we are safe because of the atmosphere.
Yes, next question.
There's one here.
Ma'am, I had doubt, and that was from in the beginning of the presentation. You showed us the X-ray image of the observable universe. You were talking about the observable universe. How does that work? I mean, the observable universe is like really large, right? So how do they get the entire X-ray image of it?
So that has been a separate and dedicated effort. Okay, so it's not just like you can send something out into space and then start seeing the X-ray sky. So that's a good question. A lot of these detectors are focused. So whenever we say it's an X-ray telescope or it's an X-ray mission, typically the agencies that are sending it out will also specify what its functions are going to be. And different space satellites have different functions. So accordingly, for mapping the X-ray sky, there was a dedicated mission sent out called eRosetta. And it had this special function of being able to see different patches of the sky very fast and at high resolution, so very well, and then patching it all together to make an all-sky image. If you remember the visible sky, then that also is quite difficult. So they sent out a dedicated satellite called Gaia to do all of these studies, basically, for the visible also.
Thank you.
Good morning, ma'am. Good morning, everyone. Ma'am, could you please elaborate upon the working of an X-ray telescope?
Yeah, so I think I showed two different X-ray detectors, like he said, based on what function they're expected to perform, will be designed differently based on what you expect from them. A lot of times, if there have been several advances made in the X-ray field, for instance, then you might be more confident again, so you will come up a better designed X-ray detector. In the initial stages, they weren't quite sure, so they were going with slightly different instruments just to take a feel for whether this field really merits more attention. So again, it's specific, purpose specific. The two I showed here are the ones which I find most interesting. The first one was like a textbook image, if you remember, and it had all of these concentric circles. Yeah, this one. Upper right. So this is from my own textbook, actually. I had to study this as part of my syllabus for my master's degree. This is a type of imaging X-ray telescope. With X-rays, it's hard to build a normal telescope because X-rays penetrate through stuff, which is why they're able to see a person's bones when they expose you to radiation, but they get halted at bones because they're higher density. So a similar thing is applied here, where you have something called, if you see here, grazing incidence optics. You need not go into the technicalities right now, but each one of these plates tries to bend the X-rays slightly in order to form an image over here. You cannot have a normal telescope because otherwise the X-rays will just pass through it. So it has to be done slightly differently. Again, there was a second detector which I showed while showing the photon nature. That was a payload on AstroSat. It's called LAX-PC, Large Area X-ray Proportional Counter, which should directly is the 5-word answer to your question. That is what is known as proportional counters. These are heavily used in high energy studies, but this one is specifically rendered to catching X-rays from the sky. So that one has it's an electrical setup and it uses all of these gases and all. I won't go into the details, but eventually it will come into your syllabus itself formally at higher studies. But what a proportional counter will essentially do is that every photon that comes in, it will generate a reaction inside the counter and then you get to see that reaction outside. Okay, so you know an X-ray has come. And this counter will measure different characteristics of the X-ray photon again. Every time I say photon, you can just think of it like a cricket ball. And the proportional counter will measure how energetic it was, from where it came, at what point it was detected, at what location in the counter did the reaction start, etc. So depends on what you're trying to do with the X-ray telescope. Like your medical X-ray scanners might be slightly different from the airport security scanners, that kind. But all of them will have to have special equipment trying to take into consideration the fact that you're working with a special type of radiation. So they will all be common in the way that they will all try to make sure that the X-rays just don't pass through directly.
I'm from Parisee. So I have a question that when you have X-rays, are those X-ray pictures satisfactory to your question? When you predicted something and the X-ray was different, so are they always satisfactory or sometimes they are different?
Oh yeah, so this simulation was just like an overall simulation of the galaxy. Like he mentioned, there are different bands that we see, and we see in like the VIBGYOR. So I will see like these are wearing green tops, there are red t-shirts here. So that is, you're dealing in the optical. Any rainbow color you see, you're using a particular wavelength. When you go into the X-rays, for instance, it's a different range altogether. There are others also, like the cell phones we use have radio wavelengths and so on. So although this was the overall picture, typically what you have in the X-rays more often than not deviates from the overall picture. Okay? If you specifically have an X-ray expectation, then it might match. But if you have an overall expectation, then the X-rays will typically map out the most energetic processes which are happening here. So here if you see, there is a central black hole-like thing, and there are wings around this. So here the X-rays will show the central object very prominently, because that is where the most energetic X-rays are coming from, and then they will like reduce, like dim slightly towards the edges where the physical processes may not be that energetic in their nature. So that's why I like X-rays, because they give you all the interesting stuff. If you even see here, for instance, this is the overall Crab Nebula across all wavelengths or all bands, and this only when we see in the X-rays, you only see like this is very zoomed in, and it's only for the like very central part of this. So I wouldn't say they deviate in a way where they give us additional information, but not in a way where we don't understand them enough, because we are not specifically always sometimes model how the X-ray image expectation would be. So the overall picture matters, and I'm just showing you how the high energy one contributes to the overall one. And if we didn't have this at all, then we would have lost a lot of information. The overall picture, the X-rays contribute to the overall picture, right? So they show you the most energetic phenomenon happening there.
Ma'am, in previous few questions, you said that we see from X-rays because of atmosphere. So due to the increase in global warming, the ozone layer is getting damaged. So in few years, would the X-rays reach to us, and in what way will it affect us?
Yeah, so I haven't really seen any discussions on this, because I'm not sure whether the blocking is coming solely from ozone. I'll have to check that part. Yeah, but there have not been any concerns raised for now on that front. So it's a nice line of thought.
Thank you.
Yeah.
Yes. Cheers.
Good morning, ma'am.
Good morning.
I'm from High School. My question is that in what all ways can the study of X-ray sky help us?
Yeah, so that was the applications of X-ray astronomy by the IAU, which I asked to take a look at, asked you to take a look at. In there, they specifically mentioned that advances in X-ray astronomy have helped us tackle the challenge of the very nature of X-rays themselves and how highly energetic they are and how differently they behave from the rest of the wavelength that you typically deal with. And the way I introduced you was from what you would be familiar with to astronomy with X-rays, but it actually happened the other way around, where X-rays were discovered first, then astronomy was done with them, and that led to more technological improvements in our applications of X-rays to human society. Like the discovery of X-rays, if you know, the first Nobel Prize I mentioned was with X-rays, and then Marie Curie tried to emphasize how they could be used for human health industry, basically, or diagnosis. And that the application part can only happen once the discovery has been done and you know of these X-rays, and the scientist has to think about what its possible applications would be and demonstrate that it would be healthy and constructive without any less side effects. So similarly, advancements in X-ray astronomy led to advancements in development of X-ray technology for doing all of this X-ray astronomy, and they eventually helped further some of these areas more. So the IU documentation that I showed here, it specifically enlists two direct merits of X-ray astronomy, being applications to medicine, like I said, and applications to airport security. And based on where pure science takes us, because as you know more and more about the universe, your knowledge is increasing, plus to get to that point, you have to push your frontiers of technology as well. And then overall, you can then, once new knowledge is created, you can think of ways in which it might be applicable to human society. So that part slightly comes towards the later end, but I enlisted two, for instance, which have been formally put out.
Okay, we have two more questions.
So, how does X-ray imaging work, or does it work like LiDAR?
No. So like I showed you with the grazing incidence telescope, there are like these concentric plates that slightly bend the X-ray light and then try to converge them to a common point and focus them, basically, because they're short wavelength, so you can't really do it this way. They're like conical telescopes with a long length.
Okay, we'll take one last question.
I'm unable to hear you. Yeah. Okay. Yeah, so the path that we took was you go up till 10th, then you, if you choose the science stream, then you will specialize in science stream up till 12th. And then you might want to take relevant subjects within your undergraduate degree, then master in them through your post-graduation degree, and you will be permitted to formally work on them during your doctoral degree, and hopefully it will be rewarding for you. Good morning.
My question is that after mapping the rays or energy, can we connect it and use it on the Earth as a source of energy?
I think when the detector detects it, it ends up losing all of its energy. Like I think somebody else asked about when I spoke about the proportional counter, the energy is lost in triggering this reaction that takes place within the proportional counter. So I'm not sure there's any left for us to utilize. It kind of gets dissipated within the counter, and based on how much energy gets dissipated is how we measure how much of it was there in the beginning. So essentially we measure the loss of energy, so it's lost.
Yeah, students need to be quiet for a few more minutes. Okay?
Yeah, we can take as many as you like.
One last question we can take. Tushar, we can go there. Either one of them.
Why didn't you raise your hand before?
Hello everyone. What are any other economic uses of X-ray apart from medical and research purposes?
Yeah, so these are pure research topics. So they are typically done for the pursuit of knowledge, and their applications, it takes some time for their applications to be tangible. This is in different fields. So different fields will have different applications, but all of these go hand in hand. So other than these, I don't see any formally listed, and we can always have surprises coming up because those require technological advancements. Again, that is not an astronomer's main purpose. But since this question was overlapping with the previous question, I just feel maybe we could take another question again, but because I've already tried to address the applications part.
Okay, so students, I think we have multiple questions about the application. And,
yeah, please take a look at this.
Yes, be quiet there. Yes, those are at the very end, those are sitting, please be quiet. So everyone is looking at you, yes, there are people at the corner. Thank you. Okay, yes, so this is a very interesting book. You can please go through this because how all these things, whatever we are talking about is very cutting-edge research. And how it is helpful in our society and how it is useful here is been listed here. So you should go through these things, okay, and then you will get more interested in what these X-rays are or what the other technologies are being helpful here. So right now what we will do is that right now we have enough questions and we had a wonderful talk with Parisee. So let us thank the speaker for this wonderful talk. Thank you so much for that.